Welcome, everybody, to the ASV and ASSA's Vic South Star Party live stream. My name is Kim Thalasudis. I'm the president of the ASSA, and today Rod Hill is joining us. Got the wrong Rod there. Before we start, I would like to say that in the spirit of reconciliation, our astronomical societies acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander peoples today. All right, welcome Rod again. I'll get the right Rod now. Rod Hill, how are you this morning?
Or this afternoon? I'm good, thanks Kim. Thank you, and welcome to everyone watching.
Right, so today you are presenting on solar eclipses, which I know is a particular passion of yours. So I'll just give a brief introduction about you, and then we'll get right into the presentation. How's that?
Sounds good.
All right. So you've had a lifelong passion for astronomy and also a very successful career as an accomplished scientist with a Doctor of Science, PhD and Bachelor of Science degrees from the then Department of Geology and Mineralogy at the University of Adelaide. You're a former Chief Research Scientist and Group Executive at CSIRO and Pro Vice Chancellor at Monash University in Victoria. While at CSIRO, you had overall management responsibility for the Australian Telescope National Facilities at Parkes and Narrabri, and you're also involved in Australia's bid to host the Square Kilometre Array, which is very impressive. You're also a fellow of several professional organisations in the minerals and chemistry domains, and you even have a mineral, Hillite, named after yourself, which is a great honour. And you published more than 100 research papers and several book chapters. And your passion for astronomy has been one that you've had since very early in your life. And you've actually built two 6-inch Newtonian telescopes. And you currently own an 8-inch Schmidt-Cassegrain. And with respect to today's presentation, you've also seen a total of, 9 total solar eclipses and 1 annular solar eclipse. So you're a bona fide solar eclipse chaser. All right, so today you're talking to us about solar eclipses and upcoming total eclipses visible from Australia. Have I got that mostly right, Rod?
Yeah, that's pretty good. Thanks, Kim.
All right. Without further ado, I'll add your presentation to the stream, and I encourage people to ask questions, make comments throughout the show. We'll ask all the questions right at the end, and I'm sure he'll do his very best to answer every single one of them. All right, so I'll hand over to you, Rod, as your presentation is now on screen. Over to you.
Thanks, Kim, and welcome again to everyone. Yes, now looking at it, as the two Ronnies used to say, I've got a packed program here, so we'll get straight into it, if that's all right. Solar eclipses. In astronomy, an eclipse is defined, in the general sense, is defined as an alignment of celestial bodies such that the shadow of one passes over the surface of another, thereby partially or totally obscuring it. Now, eclipses lie in the middle of a continuum between what we know as occultations and transits. I'll explain a little bit in this diagram. So on the left, you've got a foreground object, grey, in this case representing the moon, much bigger than the background object, in that case a star, but it could be a planet, and that's an occultation. The foreground object is much bigger than the background object and completely obscures it for some time. Then on the right-hand side, you've got the other extreme, which is a transit, where the foreground object, now the black dot, is much smaller than the background object, in this case a yellow disk representing the sun. And that often happens well, not often, because for inner planets at least, Mercury and Venus, doesn't happen very often, but it sometimes happens with asteroids and other things. And of course you get transits of the International Space Station across the moon and the sun, which people are fond of photographing. In the middle of that, the foreground and that diagram, the foreground and the background objects are more or less the same size. If the foreground, and they're called eclipses then. If the foreground object is slightly bigger than the background object, we get what's called a total solar eclipse, where the outline of the sun is a yellow dashed line in the background. And then if the foreground object is just slightly smaller than the background object, we get what's called an annular solar eclipse. Now, these I photographed these things over the last few years. An example, of course, of an occultation is Saturn in 2014, seen there disappearing behind the moon. An example of an eclipse there is the one I took in Libya, in the deserts of Libya back in 2006, with a beautiful corona showing. An example of an annular eclipse taken near Tennant Creek in the Northern Territory in 2013 there in the next one. And then finally, this is a photo of the quite rare transits of Venus, the last one of which occurred in 2012 that I photographed. So the point is, eclipses are just one of a spectrum of two bodies, celestial bodies, passing in front or behind each other. There are many different sorts of eclipses too. Of course, of the sun, I've shown you, there's one I took in Svalbard near the North Pole in 2015. But of course, many of you will have enjoyed watching transits transits of the Galilean satellites of Jupiter across the cloud tops. Here you've got Io and its shadow passing across. And if you were standing on or sitting or floating in the cloud tops of Jupiter in that shadow, you'd be seeing a total eclipse of the sun from Jupiter. Of course, there are eclipses of the moon. We've got one coming up later in November this year. November the 19th, in fact. That's a photo I took of one from my former house property in Metcalfe, Victoria in 2014. And you also get, as I've just indicated, eclipses of satellites of the planets. Now I'll talk about this sort of diagram a bit more in detail, but it shows all of the possibilities of eclipses, occultations, and transits of the satellites of Jupiter. But you can get some really unusual eclipses. This is a case back in 2009 where Io's shadow passed across, there's Io, passed across Ganymede, a very rare event. So if you were sitting in a spaceship on Ganymede, you would have seen an eclipse of the sun by another satellite of Jupiter, Io. So the interesting sort of stuff. So what's all the fuss about with eclipses? Why do people like me travel all around the world to the most exotic places and have all sorts of adventures to see these things? Well, they're spectacularly beautiful for a start. To see them often requires travels to very exotic places. Interesting things happen to the local environment during an eclipse, which I'll talk about in a minute. And they have provided some fabulous science, all of which I will also talk about. And finally, they are very addictive. So here's an example of a foreground shot of the eclipse that I saw in Uganda in November 2013 at mid-eclipse. This was in fact taken with an iPhone. My wife took that with an iPhone. And you can see the shadow of the moon, the conical shadow of the moon, projected onto this light upper level cloud all around the sun's disk. Really spectacular. And this is the group of people, obviously all looking upwards and towards the eclipse at the time. Progress of a total solar eclipse. This is the composite image that I've made of the progress of the eclipse in Svalbard, Norway in 2015. Things start slowly with eclipses and then accelerate rapidly in the lead up to totality. Those first 8 or so images are taken at 10-minute intervals, and then these last two are only 2 seconds apart. So things happen very quickly around here. I'll talk about the diamond ring in a minute and the corona. Totality for solar eclipses is an ephemeral thing. It can only ever, through celestial mechanics, be less than 7 minutes, 7.5 minutes long. Mostly they're only about 2 to 2.5 minutes long, and sometimes they're vanishingly small. Again, I'll talk about that in a minute. This is a beautiful shot by Aubrey Geminignani in Oregon in 2017, a time-lapse photo of the beginning of the eclipse through to totality, and then as the moon slowly recedes from the surface of the sun, finally comes back to normal over here. A beautiful photograph. So the preamble to the main event is the hour or so before totality, when the moon is slowly at 15 degrees, half a degree an hour, moving across the face of the sun. Strange things happen in the observer's environment during this hour or so. This is a picture of the landscape near Palmerville in Queensland for the eclipse there in 2012, I think it was. at about 80% coverage of the sun. And then when you get to totality, you get this wonderful twilight effect with the horizon, not just as you normally see in the west during a sunset or in the east during sunrise, but it's all around you, 360 degrees around. This is the part of the landscape that's still getting sunlight, whereas you're standing in the shadow of the moon here. It goes to this eerie, beautiful cobalt blue sky. Strange things happen with shadows too. This is a photograph I took of my wife and myself during the eclipse in 2017 in the US. And if you look at the shadows of me here, I'm not sure whether it's entirely visible, but some of the shadows are blurred, like around here, but other shadows are very sharp. In fact, the shadows are so sharp that you can see the individual hairs on your head or on your arms. It's a unique shadow effect that only occurs during a total solar eclipse when you're at the crescent phase, where the width of the sun illuminating shadows in that particular orientation indicated by the arrows related to this position of the sun is so small that the definition of the shadow becomes sharp. It's an eerie effect. Also, you get these mysterious dancing shadow bands that happen from the same effect that you get at the bottom of a swimming pool or in the twinkling of the stars. These beautiful black and white fringes representing differential reflection through the atmosphere dance across the surface of the whatever you're standing on, if it's smooth and white enough. The main event then comes, you're into totality. This is the first image of the main event, the sun's corona, something you can only see during a total solar eclipse unless you're using something like a coronagraph. This is the 2 million degree centigrade atmosphere of the sun following the magnetic field lines of the Earth, of the sun and being illuminated by the effect of the magnetic fields of the sun. And this is where you get that idea of a black bullet hole in the sky with this shatter cone around it. You also have the unusual situation in this case of occasionally seeing stars and planets or even comets that are close to the sun. This is Regulus, Alpha Leonis, that was only a couple of degrees away from the sun, and it suddenly appeared during the day. Now, I stop here for a moment because this is the background to one of the first proof of Einstein's theory of relativity, because you may recall he predicted that light would be bent by a very strong gravitational field. In fact, it's not well known that Newton's theory also predicts a bending of light by gravity, but at the wrong magnitude, only about half what Einstein predicted. So in 2019, during the eclipse of 29th of May, astronomers went to various places around the world and measured the positions of stars. The apparent position would be here, but because of the sun's gravity, the light is bent away from its, the actual position is here, but because of light's gravity, it's bent, and so it appears to be here. And by measuring that angular distance, they could put a quantitative test on Einstein's theory of relativity, and lo and behold, he got it absolutely spot on. And from that point forward, he was an international sensation. And there's been more recent proofs of his various other aspects of his theory, but this was the first one. And lo and behold, it happened during an eclipse. It was able to be done by an eclipse. Now, you're to be aware that the sun's activity changes according to a cycle of sunspots, and it turns out that the corona changes in its extent and degree of uniformity around the disk of the sun, depending upon what part of the activity cycle of the sun it's in. These are 4 photographs I've taken at eclipses, and I've mapped them back to their position on their position on the sunspot's activity cycle. And you'll see that the Seduna eclipse and the Uganda eclipse that I saw, the corona is very compact and circular, whereas in the Libyan eclipse and Jackson, occurring at a lower point in the activity cycle, somewhat counterintuitively, the corona is these beautiful bow tie, so-called bow tie situations, or very extended streamers. Beautiful to behold. And that's one of the things that's uncertain about every eclipse you go to. It can be quite different in appearance. Second, the main event now, moving away from the corona to the diamond ring. This is a classic photo of a diamond ring where the appearance of the inner corona around the main body of the sun and moon's silhouette forms the ring. and the last vestige of the sun's photosphere peeking through valleys on the edge of the moon produces the diamond of the diamond ring. This was the photograph taken at Palmerville in 2012. Another beautiful thing that you can photograph during a total solar eclipse is Bailey's beads. Here's again, they're peeking through valleys on the edge of the moon here, and a couple of big ones, a string of big ones there, and an isolated Bailey's bead there. If there's one left, it becomes the diamond ring. Here's a close-up of the string of Bailey's beads and a beautiful big prominence that's visible here during the 2016 eclipse in Sulawesi, Indonesia. This is about 50,000 kilometers high coming off the sun, and you can also see bits and pieces of the photosphere of the sun and little bits of the chromosphere too. Of course, solar eclipses can also be annular in nature, where the moon's angular size in the sky is less than that of the sun, so it never completely covers it, and you've got to use solar filters all the time. This is a progressive photograph I took near a place called Attack Creek, 70 k's north of Tennant Creek in 2013. This is a photograph just as the sun rose, with a little chunk taken out of the moon, and then for the next couple of hours the sun and moon pair rose in the sky, and at the same time the moon slowly descended over the disk of the sun. Here it is nearly covered. I was standing right on the center line, so I got something that was totally symmetric. Looks artificial, but you can see from this progression of shots that it moves towards totality, and then as the moon slowly moves off the sun's disk to downwards, you end up exposing the whole of the sun's photosphere. Beautiful occasion, but you can't see the corona because you've still got some of the sun's surface exposed, and it's too bright to see the corona. So how do they form? Eclipses are all about shadows. If you've got a point source of light impacting upon a body here of finite size, you only generate one type of shadow. It's called the umbra, or the central part. If you're in the umbra, you can't see any of the source. If the source of light is bigger, it's not a point source, but it's smaller in size than the object, then you get two sorts of shadows. You still get the umbra, from which point you can't see any of the source. But if you're in the penumbra, the side bit of the shadow, if you're in that, you can still see some of the sun, some of the source. If in the third and last case, the light source is larger than the object being illuminated, and this of course is the case where you've got the sun and the earth, or the sun and the moon, you get three sorts of shadows. You still have the umbra and the penumbra, but you get this anti-umbra or antumbra, or negative shadow, which is after the crossover point of the umbra. From this point, if you're standing in this part, the object never fully covers the sun, and you get annular eclipses. From here, you partially see the sun, and you get a partial eclipse, and from in here, you see a total eclipse. So it's the formation of these three shadows that determines what sort of solar eclipse you'll see. Now, a bit more detail here. Here's the sun, the orbit of the Earth. This is the Earth and its umbra. That extends 1.4 million light years away from the Earth. You've got the orbit of the moon. And of course, when the moon's in the orbit, it also has its own umbra. And when it moves around to a position here, you get the shadow, the umbra of the moon hitting the Earth just. I'll go into that in a minute. And you get a solar eclipse. When the moon, the eclipse is visible only over a very narrow path across the surface of the Earth, because it just happens that the length of that umbra is about the same distance as the distance from the moon to the Earth. If, on the other hand, 2 weeks later, the moon has moved around to the other side of the Earth, you get the appropriate geometry for a lunar eclipse, and you can see the Earth's umbra lies within the moon's umbra lies within the Earth's umbra. But you can see here the big difference here from a solar eclipse is that because the Earth's umbra is much longer and wider than that of the moon, it's anyone sitting on any part of the night side of the Earth can see a lunar eclipse. Whereas, as we saw before, if it's a solar eclipse, only a very narrow path of the shadow across the Earth allows only people within that narrow path to see a solar eclipse. Hope that's clear. So the moon's umbra only just reaches the Earth. This is a photograph from the Meteosat 8 of the eclipse in 29th of March 2006 over Libya. My wife and I were actually right there in the middle of the umbra at the time. The umbra is only just reaches the Earth there, and so we had to be right within that. The penumbra of the Earth is much wider, so anyone on the surface of the Earth in this area can see a partial eclipse, but only people there can see a full eclipse. And now here's an interesting photograph. You're looking along the shadow of the moon here from the Longjian 2 satellite orbiting the moon, looking back towards the Earth, and during a total solar eclipse, and you see the shadow of the moon coming from here and impacting on a small dot on the surface of the Earth. So at this time in the history of the solar system, the ratio of the sizes and the distances from the Earth of the sun and moon are quite similar. You see here the sun and moon diameters are this and this. The ratio is 400. The average distance from the Earth is this and this, and that ratio is 390. Because they're very similar, the angular size of the sun and the moon are about the same, about a half a degree or 30 to 31 minutes of arc. It's that peculiar arrangement, that's the peculiar arrangement that enables us to see spectacular total solar eclipses. So just a recap, sun, moon, Earth. If you're in the umbra here, you see a total solar eclipse and the corona, maximum length of that 7.5 minutes. If you're in the outer, if in the penumbra, the outer part of the moon shadow, you see a partial eclipse, and you see that for about an hour before and after the total eclipse. And if you're outside that area, you don't see an eclipse. For a recap for annular eclipses, similar situation, but now the moon is further away, and so the umbra finishes before it reaches the Earth's surface, and you see an annular eclipse if you're standing in the antumbra. You see something like this. The maximum length of that sort of eclipse, an annular eclipse, is 12.5 minutes, can't be any longer, mostly a lot shorter. If you're out in the penumbra, you see a similar partial eclipse to a total eclipse, as you see when you're out in the penumbra of a total eclipse. And if you're outside that area, you can't see anything again. Okay, so why not a solar and a lunar eclipse every month at new moon and or full moon? Well, the reason is because the moon's orbit is inclined at an angle to the orbit of the Earth by about 5 degrees. And you can only get an eclipse when the Earth, moon, and sun line up. So you have to have the node or the crossover points of the moon's orbit with the Earth's orbit lining up to a time of new moon or full moon, more or less, to get an eclipse. They have to be pretty closely aligned to get a total eclipse within 5, but they can be a little more misaligned and you still see a partial eclipse. I hope you can understand why. So you only get an eclipse because the new moon and the full moon need to occur close to the time when the moon's orbit crosses the Earth's. So where can we see an eclipse over the next 20 years? This is a map of the blue tracks represent the path across the Earth's surface of the pointy bit of the moon's umbra. So if you're standing anywhere along one of these blue lines, you see a total solar eclipse. Now the reason why they're long is because while the moon is transiting the sun, the Earth is rotating underneath the shadow, and so it's not a fixed point on the Earth, it tracks with the rotation of the Earth and, of course, the revolution of the moon. The red paths here are corresponding tracks of an annular eclipse path over the same 20 years. Now, if I plot that over the next eclipse paths over the next 1,000 years, you see that eclipses eventually come to every place on Earth. That is a map, not just for 20 years like this diagram, but for 1,000 years. And so from 1,000 to 2,000 Common Era. So you see, except for these little white spots, which would eventually be covered if you had maybe 1,500 years of eclipses, You can be standing anywhere in the Earth and an eclipse will eventually come to you. It'll come back to you about, on average, only every 375 years, though, so you can't hang around. If you want to see an eclipse, you've got to go places. Unlike a lunar eclipse, of course, where I've just explained, you can see that from anywhere on the night side of the surface of the Earth, so they occur as a result, or at least they don't occur more frequently, they can be seen more frequently. So just to point to the future, this little plot here is concentrating on Australia, and I've just magnified it up a bit there. There's an interesting few years coming up for us in terms of eclipses, and I'll come back to that in a moment. So the time and length distribution of total annular eclipses here, I've plotted them for the past 100 years and the next 100 years, or the past 120 and the next 80. And you see, the first thing you see about here is that they come in in regular repeating patterns. It turns out that pattern is an 18-year repeat pattern, and it's called the Saros. And it was the recognition of that repetition pattern and others, which I won't go into here, that enabled ancient astronomers, for thousands of years, if they had enough records of eclipses like this, they could see these patterns, and that enabled them, much to the agreement of their king or their whatever to whom they reported, political head to whom they reported. It was very good for that king to be warned of these things, because they could use it to keep their subjects at bay and show their power. We now, of course, are able to predict eclipses because of Newtonian mechanics to within about a second of time accuracy, and within a couple of 100 meters on the surface of the Earth, for thousands of years into the past and thousands of years into the future. So a common question is, does the special relationship between the apparent sizes of the sun and moon pertain to satellites on other planets, or are we the only place in the solar system that can enjoy these beautiful total solar eclipses? Well, what evidence do we have so far? Well, this is an annular eclipse transit of the sun by Phobos, the larger of Mars's two moons, as you'll all be aware. Image taken by the Curiosity rover, NASA's Curiosity rover in August 2013. That's about a 7-second interval from the left image to the right image. So Phobos, you can't be looking away during this. It doesn't last for very long. But that's an example of an extreme annular eclipse on Mars produced by Phobos. We've already seen this diagram. If you're here, it's a totally. If you're standing on that point in the shadow of Io, you would be seeing a total eclipse of the sun. So we have evidence they occur elsewhere. And of course, I've already explained this diagram. You get all sorts of interesting things happening here. The Io, if we're watching it from the Earth here, we see the Io's shadow transiting across Jupiter. If we're looking at the satellite itself, we've seen Europa starting to transit across the disk of Jupiter. We look at Ganymede here, and it's about to enter the shadow of Jupiter, so it's being eclipsed. And finally, Callisto, it's about to enter behind the region behind Jupiter that's out of our line of sight, so it's being occulted. So Jupiter shows all these things, and you can watch them through your own telescope in real time. But we're also in this is a photograph of the solar corona and the moon's silhouette taken by Buzz Aldrin on the Apollo 11 spacecraft during their translunar coast prior to lunar orbit insertion in July 1969. Photograph courtesy of NASA archive. But predicting the characteristics of eclipses on other bodies of the solar system, I did some work a few years ago on this. I calculated the characteristics of the 156 named natural satellites or moons of planets and dwarf planets in the solar system. These are the ones I looked at. I won't bore you with the detail here. I used the furthest and closest distances of the moon from the planet, the diameters, the eccentricity, the rotation and revolution periods, and the position of the observer on the planet's surface to calculate what it would whether you could see eclipses. The critical parameter that I used with this so-called ratio R of the apparent diameter of the moon in arc seconds over the apparent diameter of the sun at that point in the solar system on that particular planet or dwarf planet. And if R is greater than 1, then you get a total eclipse because the size of the moon is larger than the sun. If it's less than 1, you get an annular eclipse or a transit because it's smaller than the sun. And I'll just re-emphasize here, the unique situation with respect to the solar system and our position here on Earth is that for our Earth, Moon, Sun system, R has values in this very restricted range. The R value when the moon is farthest away from us and the sun is closest is 0.92, and the R value, maximum R value when the moon is closest to and the sun is farthest away is only 1.09. This is why we can flop between annular eclipses and total solar eclipses. And that's pretty special. So this is the plot I had. This is the actual size of the satellite. These are all the 156 satellites of the different planets and dwarf planets. This is the R ratio. And so I've arbitrarily assigned this gap here between an R value of 0.4 and 1.2 to define annular eclipses and total solar eclipses that bear some close relationship to those on Earth. You'll see the moon, for obvious reasons, plots right in them almost exactly on the R equals 1 line. Anything over here is an occultation because the moon is much bigger than the sun. Anything over here is a transit because the moon is much smaller than the sun from that location. So the 5 Earth-like total eclipses in the solar system. This is a photo of the one you've seen before today at mid-totality in the United States 4 years ago. And these are my simulations scaled to the same size and the same corona as I photographed for the USA eclipse, but with the scaled size of the moon, the planet's moon, not our moon, but the planet's moon, in this case Callisto, and in this case Epimetheus on Saturn. And you see that these two bear quite similar, especially Epimetheus on Saturn. There's a close relationship to that of the Earth. So that's a pretty good, if you were there on the cloud tops of Saturn and Epimetheus was in the right place, you'd see an eclipse quite similar to what we see on Earth. Another couple of situations here. There's this Perdita on Uranus, and of course some of these satellites are quite eccentric, so their size changes. This is when it's farthest away from Saturn at periapsis, and here it is, closest, and this is its furthest away. So you'd flip between, for this particular satellite, you'd flip between seeing what I call a split annular eclipse and a total eclipse. Super total eclipses occur when R is much greater than 2, and this is a case. Ganymede sits here on my plot, and you'd see if an eclipse by Ganymede, of the sun by Ganymede, you wouldn't see any of the corona. It wouldn't be very spectacular at all. All the other 38 satellites with R greater than eclipse produce occultations, which can be up to 300 times the size of the angular size of the sun in the sky. So they're not very spectacular at all, and often too small to see. What about the 10 annular eclipses in the solar system that approximate those on Earth? Again, the same deal, scaled here to this mid-annular eclipse that I saw near Tennant Creek in 2013. That's the actual photograph. Here are the scaled, same size of the sun as here, with the moon of the under consideration scaled to match the same as the Earth. This is Cupid on Uranus at its furthest position from Uranus, and this is the eclipse when it's in part of its orbit that's farthest away. Here's the Phobos situation, and just so you know, I didn't make these numbers up. Just let's remember that was the photograph taken by Curiosity. So I'll swear on a stack of Bibles here, or the Quran, or whatever, that these were the simulations I did, and they came out, and when I checked them, this is what they compared with. So I'm pretty pleased with that. And even the timing, it was going to take about 10 seconds to cross across the image of the sun, and this takes 7 seconds. So I'm confident of the calculations. Super annular eclipses, what I call these, when R is much less than 0.4, and the classic case of that is the transit here of Venus across the sun, and the R value for Venus there is 0.03, and if I find the nearest satellite that matches that, it would be Sycorax on Uranus, and its annular transits would look like this. So the remaining 105 satellites with R much less than that produce transits, where they're much, much smaller than and in many cases, vanishingly small. What do they look like? Relative sizes of eclipses on other planets. This is the total eclipse on in the United States, and scaled in the sky, you see that Phobos comes closest to the size, but then the further you go out in the solar system, the smaller the sun's disk becomes, to the point where on Pluto, this is Styx eclipsing the sun from the surface of Pluto, and it's vanishingly small. You need a telescope to actually tell that something was actually happening, and so forth and so on. So I think the bottom line is clear. Eclipses are quite spectacular on Earth, and nothing really matches them, largely because we're the closest planet to the sun that has a moon. We live in a unique period also in the solar system's history, because the moon, as you know, is retreating by about 3.8 centimetres from us every year due to tidal forces. And so we happen to be living in a time here when the distance of the moon produces a window of between the moon's maximum and minimum sizes and the current average position of the moon and the sun's maximum and minimum size. So we can see annular and total eclipses together while in this period on Earth at which we live. If we'd lived, if we had lived on Earth 480 million years ago, there would be nothing but total eclipses. There wouldn't have been any annuals. If we want to wait a few more million years to 960 million years from now, all of the totals will disappear and we'll only have annular eclipses. So we're really living in a quite unique time. Total lunar eclipses will not be visible, by the way, just as an aside. It'll eventually move beyond the extent of the Earth's umbra in about 27 billion years. So I don't think we need to worry about that one. Okay, future total solar eclipses. We're on the home stretch here. You've seen this photo before. I've shown you the concentration on Australia. Here it is again. But let's first start with partial eclipses, for completeness. The next big event is 4th of December this year. It's actually a total eclipse, but it falls over Antarctica. So in Australia, Tasmania and very, very southern parts of Victoria will see an eclipse, but its magnitude or the proportion of the sun's disk that's covered is only between 0 and 5%. This is the eclipse I'm talking about. The path of totality is around Antarctica, and we just see a tiny bit of it in the very southernmost portion of Australia. Here's a simulation of what it will look like from Astronomy Yearbook 2021. From Melbourne, you'll just see a little chink. From Tasmania, a little bit more, but it's only a very low penetration partial eclipse. The next ones are then 21st of May, where there's a bit more coverage. Western Australia will enjoy that. 9th of March, partial. There will almost be a total in Queensland, New South Wales and Victoria, but still only a partial eclipse. And then there's a couple of other ones with very low coverages in Tasmanian Vic and South Australia, etc., in 36 and 40. Okay, enough of partials. They're not the main event. Here we go. The next one in Australia is the hybrid total eclipse on the 20th of April 2023. This is the path of totality here. It just clips the westernmost part of Western Australia, goes across East Timor and Irian Jaya before petering out north of New Zealand. The cloud prospects are very good for that one, as usual in Australia at that time of the year, blue being very little cloud cover and orange being slightly less optimistic. And this is the detailed path. This is the only bit that crosses Australia. This is the Exmouth Peninsula. This is the Cape Range. This is Exmouth here. And this is Learmonth. And the centre line crosses across here, nearly gets through Yardie Creek, and the extent of the totality path almost reaches out to the edge of the Exmouth Peninsula and almost into the bottom part of Exmouth Gulf. So this is the place to be in April 2023 if you want to not travel overseas. The next local one is, you got to wait till 2028, but this is going to be brilliant. This is 5 minutes and 10 seconds long, and it goes right over the Kimberleys and right over Sydney. There's the weather map again, and this is the track. Goes right through Central Australia, and then you can see here is almost exactly over Sydney, and certainly takes in a lot of the very populated north and southern suburbs, as well as, of course, this big track inland. That'll be a brilliant one. It's a long one. It's over 5 minutes, quite rare. Next one after that, 25th of November 2030. We just clipped the end of it now here. The main track starts off the western coast of southern Africa, goes right across the Indian Ocean, and then clips, almost goes back to Ceduna, but not quite, and then peters out before it gets to the east coast. This is the path up to the end. It goes just south of Ceduna and north of Port Augusta, across and peters out somewhere around in here when the sun sets. That'll be another good one. It's 3 minutes and 44 seconds if you're here. It'll be a bit less if you're in somewhere in this range, probably a minute and a half or so, and then petering out to nothing at the end. But worth journeying to have a look at. The one after that, 13th of July 2037. This is its path here from the southern Indian Ocean across to east of New Zealand. Crosses across almost the midpoint of Australia, and its point of greatest eclipse is in the middle of the continent. Here we go with the main path, just by Geraldton, near Geraldton, passes close to Alice Springs. I think Alice Springs is right on the northern border, and then it goes across, centreline goes across the Gold Coast. Another wonderful opportunity for populated areas around Brisbane to see a beautiful 3 minute, nearly 4 minute total solar eclipse. And then the last one I think I'm talking about is 26th of December, Boxing Day in 2038. Another one that crosses across significant parts of southern Australia and New Zealand. It's only 2 minutes and 18 seconds, but it's the one that Victoria can enjoy. You Victorians and the South Australians get another one. Starts off here north of Exmouth again, and right through the central part of Western Australia, southern part of South Australia, and the northern Victoria and southern New South Wales. Another beautiful eclipse that's very handy for a lot of us watching here today, this presentation. So there's lots to look forward to in Australia with eclipses, both partial and, but especially total. And I'm now open to questions. Thank you.
Okay, excellent presentation, Rod. That was most informative. I mean, that was really something special. Thank you very much for putting all that information together. That was really outstanding, actually. Great explanations, not only on planet Earth, but also through the solar system, and some nice simulations. Questions, please type them into the comment field. We'll stand by while you do that. And in the meantime, I'll ask you something perhaps I don't think you covered, and that is, when did you see your first total solar eclipse?
It was
what were the circumstances?
It was a long and frustrating wait. I saw my first partial eclipse when I was in high school, projected from my telescope, and I'd started up an astronomical society at the school, and it had 10 very enthusiastic members. I can't say the rest of the students were so enthusiastic, but we got a little bit of a crowd. It covered out 40% of the sun. Then I waited 35 years to see my second partial eclipse, but my first total eclipse was in Ceduna in 2002. It was wonderful, wonderful experience.
No, that was particularly special as well for me. I travelled there with my son at the time, and it was I didn't know whether it was worth making the journey, given the duration was only going to be 30 seconds or thereabouts from memory, and
Yes.
And very low in the sky. But to me, it was actually quite spectacular. I mean, that bullet hole in the sky piece and being low in the sky also gave you the moon illusion effect, where the whole eclipse looked larger to the eye, or your brain sort of psychologically shows it much larger than it actually is. And that was a sensational experience. One I will remember forever. Yeah. All right. So I assume you're travelling in a couple of years' time.
Oh yes. Yeah. In fact, you have a bit of advice to people if they want to see the one in Exmouth, then you better get going soon, because there'll be literally tens of thousands of people coming from all over the world to see that one, because of the lack of landfall of the centreline. So, and the other places are, as I mentioned before, East Timor and Irian Jaya. and the cloud prospects in East Timor and Erinjai are nowhere near as good as they are in Australia. So people will be coming from everywhere just to that little place on that peninsula in Western Australia. So get your bookings in early. Make your plans now, and get it locked in, because closer to the time there won't be the same. Most places will be booked out. I've got plenty of stories sob stories about people who got pushed off, gazumped by big tour groups and things because they didn't get in early enough. So camping's probably the best strategy there, and drive in on the day, from a short distance on the day of the eclipse.
Okay, I don't see any questions coming through at the moment. I know we had some technical issues at the start there, and I have a plane taking off at the moment in the background. So if you have any questions, please type them in now. Otherwise, we're going to call it quits in a few seconds. So I don't see anything coming in, Rod. A few comments, of course. People saying thank you very much. And the sun is shining here in Adelaide, as it is indeed. I've had to move my table a couple of times while you were talking, because I'm now coming out of Eclipse, so to speak, under this tree. Right, so look, I think that's all we're going to get today, right? So look, this is recorded, and we do get a lot more people watching it after the event, and the cumulative numbers tend to go up and up. So we'll tag this one appropriately, and get a whole lot of solar eclipse people interested in solar eclipses will be watching this in future for sure. All right, well, thank you once again, Rod, for an excellent presentation, and I'll call it quits there for the day. For today, actually, we do have one more presentation later on, in a bit over an hour's time. We're streaming live images of the sun, and I know the sun is very active at the moment, so tune into that, people, and you'll see some pretty sensational images. And I think that's where we're going to end it right now. So thank you once again, Rod. Till next time.
Thanks, Kim, to the Astronomical Society of Victoria and Astronomical Society of South Australia for giving me the opportunity. It's been a real pleasure, and I hope people have enjoyed it. Thanks.
It was great. Thank you very much again. Cheers.